In this video, we're going to talk about similarity mappings. So we've been kind of working our way up to this idea in chapter 12. Now I want to kind of start it slightly discussing the problem opener for the section. I'm not quite going to do exactly what they were discussing, but I do want to look at, like, if you were to use a physical example of similarity, this could be a good idea. So let's say we start with like kind of building with some building blocks, okay? And here, I'm gonna do my best to draw a 3D figure here. All right, and here, let's say that along this side, we've stacked 2 blocks and then 3 blocks along that side. And this is kind of what we're looking at. All right. Oh, gotta like that really wavy diagonal line there. There we go. All right. It's sometimes what you can just do. Okay. Doesn't have to be perfect. But what I have created here or drawn here is the idea that I have like 2 by 3 by 1 setup. Oops. It's supposed to be by 1. A 2 by 3 by 1 setup, right? 2 blocks on one side, 3 blocks on the other, and then it's a height of 1. All right. If I'd like to scale this up, if I would like to scale up by a factor of 2, factor of 2. Wow, it's like, there we go. All right, go underneath there. Okay, so what I'm doing then is I'm basically saying that I'm going to double everything. Okay, so then rather than have just 2 blocks at the front, I would have 4 blocks at the front. And then I'd have to double the height as well. So instead of being 1 block up, it would be 2 blocks up. And then drawing backwards here, I would need to go 6 blocks this way. Okay. 1, 2, 3, 4. Let's see. 1, 2, 3, 4, 5, 6. One more. All right. And now I just got to connect all the lines here. Draw these back. And there we go. Oops. Super crooked. Sorry about that. All right. It's because this back line is so crooked. There we go. All right, it's fine. So now I've built it up to be 4 by 6 by 2. Okay. And what I've essentially done is just doubled all of the dimensions. I doubled the width, the length, and the height. Okay. That's the idea between similarity mappings. It's like we are taking something and doubling it in size or halving it or tripling it, right? The idea is we change the size by a bit and it kind of has this scale factor connection. That's similarity mappings. Anybody who's fooled around in some sort of like program that has different size pictures where you can size it how you want kind of understands how this works. So I'm going to refer to a few things again from the book to do this. Oops. I am going to probably pull a couple pictures in just because it might be really difficult to talk about without having them. But I would encourage you to write this down in your notes. We're going to look at page 843, the try it, 12.3.1. Okay. So let's see if I can do this nicely without it being too difficult. I'm going to pull in a copy of part of it. So this is technically just the first half. All right, let's see if we were able to do this. Usually when I pull in a picture, it's super big in comparison. So I'll have to size it down. All right, not as bad as it has been before. So they're giving us some pictures to look at and they're saying, okay, determine what the scale factor is. Now this is approximate, okay? We're not going to be perfect here because we're just saying approximately what it's going to look like. If I really wanted to get like a ruler and measure it in the book, I could do that. but we're going to approximate it for right now. Okay, so notice they're using that kind of indicator about which is the original versus the new one. So in the first problem here, you'll notice that one of them is A and the other, excuse me, is A prime. A prime then is supposed to be created based off of A. So the green figure here is the original one. All right. So that's the original. So they definitely shrunk it. The question is, how much does it look shrunk by, right? Like, so I'm kind of examining. Let's start with maybe the longest side here compared to this long side here. Does it look like, if I kind of followed the path, is that about half? And I would say, yeah, kind of does look like close to half, right? The idea is you're supposed to draw from, and it does. It looks like maybe this length here is about half of the length here. So I feel comfortable in saying that this is a scale factor of, there's no I there, scale factor of 1/2. Okay, let's look at the second one here. So this one, they were kind of clever, right? They tried to put one inside the other. But in this case, the green figure is the smaller one. That's the original. And the red figure, being the bigger one, is the new one. Okay. And again, it kind of feels like the side doubled, right? It kind of like I'm looking at the length of this and I'm kind of imagining if I were to line it up down here, it kind of looks like we've doubled it. All right. So I feel pretty comfortable in saying that this one is a factor of 2. Okay, so I'm going to go ahead and paste in the second version of this so we can look at the rest. And again, let me shrink it down a little and zoom back in. There we go. I just realized I covered up what I wrote there. There we go. Okay, so for the third one here, the original is the green one. And interestingly enough, the smaller one does look, I'd say, even less than half. Okay, so here, let me kind of see if I can give myself a way of measuring this. So if this right here is the length of that little line, and I were to draw it over here, I'm kind of feeling like maybe I could fit like 3 of them loosely. Kind of thinking so. So I'm kind of thinking from the original to the smaller one, that the factor might be a third. Okay. But I want to comment on the fact that there's like a flipping thing going on. And if I want to take into account that one of them is flipped from the original image, like they didn't just take it and shrink it, right? They actually flipped it too. We can use a negative to indicate that they inverted the figure as well. Okay. Really, though, I'm more interested in kind of comparing whether or not we feel like they tripled it or halved it or something like that. Okay. Okay. Looking now at number 4. Again, I feel like it's definitely bigger than a half. I just want to make sure it's not like a fourth. All right. So here, I'm going to kind of draw this again. All right. So I'm trying to compare that. Yeah. I'm feeling like it. Oops, yeah, I'm feeling like it's about a third. Okay. So again, not a third, sorry. We're blowing up the green one into the red one, so that would be a 3. No inverting, so just straight factor of 3. Okay, so that's the whole idea behind scaling factors. We'll kind of take it with a grain of salt when we don't give much information but a picture, all right? We'll approximate. Now, I would rather have a little bit more solid mathematical relationship. And that's where we're going to use the idea of similar polygons to kind of help us. Polygons. Okay. So here's what we know, excuse me, about similar polygons. 2 polygons are similar if, okay, and here's how we know they're similar. The measure of the angles remains the same. That's kind of what keeps it looking like a blown up version of the other, that the angles don't really change. Okay. But here's the other key piece. The lengths of the corresponding sides have a set ratio. So the lengths of the corresponding sides have a set ratio. Oops. Meaning, like in my first example that I did with the blocks, the ratio is 2, meaning like every side increased by 2, by a multiple of 2. Okay. So that kind of ratio that we're talking about. Let's look at some examples that hopefully aren't so involved as drawing blocks. Okay, so let's just draw some triangles here. Let's say here's my triangle, and this will be triangle A, B, C. And we happen to know this is 21 and this is 27. All right. And then I have another triangle here, smaller. And this will be D, E, F. And I happen to know that this is, excuse me, 5. And this is 7. All right. And let's say we're told triangle ABC is similar to triangle DEF. Okay. Now, there is a notation we can use for that. Let me just write that notation down. So instead of like approximate signs, it's kind of similar to it. For saying that two figures are similar, we do a single little tilde. So that means when I state it like this, I'm saying that triangle ABC is similar to triangle DEF. All right, cool. So now that I know that, here's the thing that I'd like to find. I'd like to find the missing sides. And what I'm missing up here is this side here on that triangle and this side here on this triangle. It's such a sad looking second triangle. I just realized like how terribly badly drawn that is. Yeah, all right, as best I can. Diagonals are terrible on the tablet. They just come out very squiggly. Okay, so what I want to do is compare the two sides we actually do have that are both located on the hair. So I noticed that 21 and 7 are kind of in the same corresponding location. And what I'm going to do is take the ratio of those two sides. And so I'm going to write, I'm comparing side BC to side EF, writing it in the segment notation. So that would be 21 over 7 or a ratio of 3. Compared to what we were just talking about a little bit ago, that means there's like a scale factor of 3 going on here, or 1/3, depending on which way you're looking, if you're talking about building up or shrinking. Okay. Okay. So using this, I can find the missing sides, right? So like if I'm wanting to find side AB, I need to compare it to side DE. And side DE is 5. And it's got to come out to 3. So what's AB going to be? Well, it's going to be 15. That's how I'm going to get out 3. All right. I don't really need to write it in this notation. I'm just emphasizing that we're talking about a ratio. Let's go ahead and find the side DF. That's the other missing side. And since it's from the smaller triangle, I'm basically going to take the 27 and divide it by 3. And that will give me 9. So there's AB, there's DF. I found the missing sides. And it makes sense. If I look at them up here, one triangle is 3 times the size of the other. Wonderful. It doesn't have to be triangles. We can use any polygon. I'm going to do one example with kind of a weird one, only because it's just annoying sometimes drawing some of these. Oh, here, sorry. Actually, I'm going to refer, if you don't feel like drawing this, to number 6B on page 856 in the book. I'm going to like really roughly sketch it, okay? But they've kind of got this funky figure here. All right, and they label this G, F, I, H, and this one's J in the corner. Okay. And then they tell me that this is 1, and this is 2, and this is 4. All right. And then we have a bigger version of this. Stop being so picky. I have to tell myself to stop stressing about it. Just bothers me when it looks so crappy. Okay. L, K, N, M, and this one's T. Great. Okay. Then they give us that this is 10, that this is 7.5, and this side right here, which is kind of blocked by my K and T, is 2.5. All right. And they want us to find the missing sides. By the way, they stated that these two figures are similar. Okay. So we want to find the missing sides. All right. So what I need to find here is FJ. But before I can find FJ, I need to figure out what they already have listed here that I can use. And that would be the bottom, right? The bottom two, those are corresponding. So I want to basically just take a ratio of those, LM to GH, which would be 10 to 4. And let's see, I think that's 2.5. All right. So basically what we're doing is we're taking on the smaller one, if we multiply it by 2.5, that's the scale factor. It's going to give us the bigger one. Okay. So let's use that. Actually, here, let's find KL real quick. KL. KL equals, okay, so from the smaller side, it's a 1, which I'm going to times by the scale factor of 2.5, or the ratio of 2.5. So this missing side right here is 2.5. Let's do that again for NM. So that one on the smaller one is 2. And when I times 2 by 2.5, I get 5. So that is this side here. Okay. Now to go the other direction, to go smaller, like if I wanted to find FJ, I need to divide. So I'm going to take 2.5 and divide by 2.5, and that comes out to 1. And then for JI, I'm going to take 7.5, divide it by 2.5, and that comes out to 3, which I just plugged into my calculator, by the way. That's where I'm getting that. And there we go. Okay, so that's how we could do the ratio method. There is a algebraic approach to it, by the way. If you wanted to see that, let me just kind of comment on that. So if I wanted to use like algebra to do this instead, in fact, here, let me come back up to this triangle up here. If I wanted to approach this using algebra, we would use a cross multiplication. Actually, I take it back here. Let's look at 6a. Just to look at the algebraic approach. Same section, 6a. It's triangles, so they're not too difficult to draw. Okay. There's one triangle down here, which we call triangle A, B, C, and we're told this is 12 and this is 3. I'm not drawing it perfectly because it's just not trying. Oh, but at least attempt to make them look similar. All right, there we go. This is triangle F, B, E. All right, and then we're told that this is 1, 4, and 3.5. Okay, so the only side that's missing is this side right here, side AC. So I'm going to call that X. If I wanted to take an algebra approach, what I would do is I would use the corresponding side to AC, which would be FE here, and I would make a ratio for those two. I'd say, okay, X over F is going to be the same as one of the other comparisons here. So here, we'll use the big side. Let's do, oh, I just kind of realized, I drew this badly. I did draw this a little bit off. I'm so sorry. Let me fix it. So my bad picture over here was a little bit on purpose and I didn't realize it. Okay, there we go. So that was supposed to be longer. So the corresponding side to X is not 4. It's actually up here. It's 3.5. Okay. Because I can tell that AC is smaller than BC. Okay. But on the other figure, I could tell that FE is the longest side there and BC is the longest side on the other triangle. So I apologize. I'm so sorry. Okay. So here we go. Not X over 4, X over 3.5. By the way, too, we can also look at how they listed the triangles in the similarity. Like when they stated that the two triangles were similar, they stated that triangle ABC is similar to triangle DEF. So that kind of also helps us correspond the sides. Okay, ABC, right? Going in that order, ABC, going here, 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 right? Okay. DEF, right? It's going in that order. So that helps us also compare the two sides. All right, back to the algebra here. So X over 3.5 is going to equal, okay, so here I'll use the long side this time. The same thing as 12 over 4. So I'm using the two long sides. All right, and then I can just cross multiply this to solve. So that would be X times 4, which I could just write as 4X. And then 12 times 3.5, which I'm using my calculator, that came out to 42. And then to solve this, I divide both sides by 4. And that gives me 10.5. So we can use an algebraic approach to solve these as well. All right. I did want to kind of talk about specifically with similar triangles. There's kind of like a whole way of building the theory for similar triangles based on the properties that we saw for similarity mappings. So for similar triangles, the one way we could tell two triangles are similar is if two of the angles are equal. So they call that the AA similar property. And that just basically means two angles are equal. So in a triangle, if you happen to know two of the angles are equal, then that means that all three angles are equal because we can find the third angle and it's always going to come out the same for both of them, right? If two of the triangles have two angles equal. Okay, so that's the AA similar property. The other property is when you have the three sides and they have that corresponding ratio. Okay, so this is called the triple side similar property or SSS similar property. And in this one, we're saying that the corresponding sides are proportional. Or they have the same ratio. That's what that means. Okay, so let's just look at some examples of this. If you want to go ahead and look at page 856, number 10. I'm going to do some rough sketches. Okay, we'll start with A. We might only do the first couple. Let's just see. Okay, so this one's kind of tricky because they built one triangle inside the other one. So U, V, Y, and then this one is W, X. And we're told that these angles right here are both 108 degrees. We're given that information. All right, and that's all we're given. So they're wondering, are the triangles here similar? We're trying to compare the triangle UVY, that's the smaller one, to triangle, the bigger one, UWX. UWX, okay? So the smaller one versus the bigger one. I know one of the angles are equal. This angle right here is obviously the same, okay? There is another angle, however, that's equal. And that would be the top angle because they both have U as their top vertex. So since angle U is the same for both of them, okay, these two are similar by the angle-angle property. And it's because angle U is the same on both. And they gave us the other angle. And that's all we needed. With those two pieces of information, we could say these two triangles are similar. Okay, let's look at B. So B, they kind of did an obnoxious mirror image version of this. I'll do my best. Could have been worse. Okay, so they called this 35, 48, and 50. And then this one's 32, 35, and 24. Okay, so what I have to do is compare each of these corresponding ratios. I'm sorry, I got it so close, I needed to redo it. And see if they're the same. If every single one matches, then these two triangles are similar. Okay, so here, let me also label them with the vertices A, B, C. And then this one is D, F, E. All right. Okay, so let's compare. So I'm going to take the ratio. We'll start with the biggest of the two. All right, the bottom. So I'm going to compare BC and look at its ratio over DE. All right, so I'm going to take 50 and divide it by 35, grabbing my calculator, which I have hidden under something. Here we go. All right, 50 divided by 35 gives me 1.4. 1.4. All right. Like, okay, great. I compared those two. All right. So now let's do the smallest two. Let's compare the smallest two. So that would be side AB compared to side FE. So I'm comparing the smaller sides to each other now. Okay, so AB is 35, FE is 24. So let's divide 35 by 24. 1.45. Oh, okay. So actually here, I should mention this one technically was 1.42. This one is 1.46. They're not the same. So not similar. They came out the same, it would have worked. And that's how you check. You just start dividing them. The minute one of them doesn't match, we're done. All right. Okay. Now, this can be used with actually helpful, useful applications. Okay. I want to look at number 30. I think it's a pretty decent little application. It's on page, let's see, I'm going to actually physically turn it into the book, page 860. And this one, they have like a river, and they want to measure the length of the river, which is kind of difficult. So in order to do this, instead, they used similar triangles. And what they did was they measured off a couple pieces of information here, pretending those are straight. Let me actually make it look straight here. There we go. And now I'll do my little river. Okay, great. Okay, and they say that because the two parts that are on the side of the shore of the river, it's easy to measure. They figured that this one is 7 meters. This one came out to 5 meters. And this ended up being 8 meters. And they formed two right triangles. All right. And the question kind of is, are these two triangles similar so that we can use similar triangles to help us figure out the length of the river? And the answer is, yeah, they are similar. First, I happen to know that they both have a 90-degree angle. That's already given to me. But these two angles right here, we have a name for those. Those are called vertical angles. So that means they're equal. and therefore these two triangles are similar. So what I'd like to find is the length of the river. I'll go ahead and call that side X, and I'm going to use the triangles to solve for X. I'm going to go ahead and use algebra to set this up. So I'm going to compare X to 8. Those two are the corresponding sides, okay? And that's going to compare then 7 to 5. And now I'm going to cross multiply. So X times 5 is just 5X. 8 times 7, that's 56. 56 divided by 5 is 11.2. And there we go. We were able to find the length of the river without actually having to try to go across the river. We could use similar triangles to help us create these kind of imaginary right triangles. All we need to do is make sure that what's happening here, that is a right angle. And if we set that up as a right angle and figure out how far out it would go, we would be able to actually measure the length of the river.